Hi everyone. Today I'm going to be talking to you about the sensory system in the star-nosed mole. The sensory system it primarily uses its somatic system, which is touch. Tactile foveation in the star-nosed mole was viewed. What is a star-nosed mole? They live primarily in wet soils. They eat earthworms, insect larvae, leeches, and small crustaceans. They grow to be about 15 to 20 centimeters in length, and they are functionally blind. They use that star on their face to detect anything they need to detect. Now, here's a video that I found by David Attenborough about the star-nosed mole.
A star-nosed mole, possessor of perhaps the most extraordinary nose on the planet. Its nostrils are surrounded by 22 fingers. Fingers that allow the mole to sense the world around it by touch alone. It enables it to detect food with astonishing speed.
So that was a video of the star-nosed mole, and as you can see, it could clearly use that nose to find its prey, and at a very, very fast pace. So some of the terminology used in this article was saccade, which is a jerky or rapid movement, a fovea, which gives the clearest and sharpest picture of an image, like in an eye. Therefore, the fovea allows the moles to understand what it is about to eat. And convergent evolution, which is when organisms that are not closely related independently develop similar traits. So like a human eye and the star on the mole. The star itself has 11 bilaterally symmetrical appendages for a total of 22 appendages. The tactile foveation are the pair of small 11th appendages just above the mouth. So here are the 11th appendages, and the mouth would be somewhere down here. Now, in this article, the purpose of it was to provide a description of the star's movement in response to prey items that are different sizes. The hypothesis was they wanted to see if the 11th appendage acts as the tactile fovea in the star. The bigger picture was to compare the star-nosed mole's somatosensory fovea with the visual and auditory foveas of other species, studying the degree of convergence in the design of the sensory system. So they wanted to see basically if this fovea acts similar to the fovea in a human eye or a primate eye. Now, the methods and materials that they used were 4 star-nosed moles were captured, and they were placed in 36 by 55 centimeter containers with 20 centimeters of peat moss. They were connected by a 5 centimeter plastic tube to a 26 by 40 centimeter container with about 6 centimeters of water. They were fed small crayfish and night crawlers. The sizes of these prey items range from 1 to 6 millimeters. A high-speed camera was used to catch every behavior. It was filmed at 200 to 500 frames per second and captured by iMovie, and they did about 526 behavioral trials. Here's the setup. So as you can see, here's the 5 centimeter tube with the prey item in it and the high-speed camera connected to it. Now, for their search behavior, when they were exploring and looking for food, moles made high-speed touches with 13 touches per second. Each touch lasted about 26 milliseconds. The touch was defined as a brief, firm compression of the star against an object. Each touch was followed by a saccadic movement of the nose. The movement lasted about 50 milliseconds. The unit of search behavior is a touch followed by a saccadic star movement. Totaling lasted 76 milliseconds when not in contact with any prey items. So here's the results of that. As you can see, when no prey was contacted, the touch and the saccade were fairly long, hence this is in milliseconds, so short for us, but long for the mole. When the first prey came into contact, the touch and the saccadic movement decreased. So they were faster when they came in with prey, when they came into contact with prey. Now, the results of the foveation were 100% of the trials. When food was detected, the mole made saccades that positioned the 11th appendage onto the prey item. The contact with the 11th appendage during foveation consisted of contact with the prey item. It was followed by additional exploration or eating of that prey. They found that the star-nosed mole tactile saccades to foveate prey was similar to the primate eye movement. Now, the average velocity of this was 18 centimeters per second. I have a video of what they did that I'm going to show you from YouTube. And it's right here. Now, watch very closely when you first see it. They're going to do the full recording in its regular time, and then they're going to slow it down. So as you can see, it ate that prey up very, very, very fast. Found it and ate it. Now they're going to slow it down. And as you can see, the 11th appendage right here is touching that prey item first. Or last, rather, right before it eats it. So the mouth would be right here, and the tactile fovea is right there. So there's an example of what they were doing. Actually, that was their exact footage. Now, here's the picture basically captured in picture style. So they slowed it down. The prey touched this appendage first and then moved over. And as it touched the 11th appendage, the mole would then eat it. And here's the speed at which it did it. So it started off really fast and went really slow. So it had an acceleration and a deceleration of movement. Now, the results of the distribution of the contacts with different appendages were the most contacts were made with the 11th appendage. The larger the prey got, the more appendages would touch it. The average number of contacts with the outside appendage was lower with smaller prey and increased as prey size increased. So here's the example of that in graph form. So a very, very small prey would only make contact with the 11th appendage. As the prey got larger and larger, each appendage would touch it a little bit more, but the most number of touches was always by the 11th appendage, right before it was eaten. Now, in their discussion, they concluded that there are parallels between the mechanosensory system of the mole and the visual system of other mammals. The foveation movements, so like the saccade, resemble the eye movements of more visual species. Therefore, we can refer to this movement as a saccade because it does resemble those eye movements. So the designation of the 11th appendage as a tactile fovea was indeed confirmed through the study, and the saccades lasted about 30 to 70 milliseconds, which is very similar to the movements of our human eye. The saccades have an acceleration and a deceleration just as well, like our eye. So there was evidence of convergent evolution in the design of a complex high-resolution sensory system. So the somatosensory system versus our visual system. The visual and auditory and somatosensory foveas, they do have similarities. The most obvious being that the division of the sensory system into a large low-resolution area for scanning small high-resolution area is used for detailed analysis. So the mole sees something very small, knows it's its prey, sees it in its head, and eats it. The retinal fovea and the star-nosed mole fovea act in the same way, so physical movements of the area during foveation. Now, the function of the star, they determined it can detect very small prey, which means a millimeter. It makes rapid and accurate sensory discriminations, and it is rare for the mole to miss prey once it has had contact with the star. The touching is concentrated on the 11th appendage, and it allows the mole to thrive in the environment and cover a lot of surface area when foraging for food. So this star allows it to basically, without actually seeing it, see its prey and be able to eat it and thrive in its environment. I personally would like to see if the mole can distinguish between prey it wants and prey it doesn't want. So let's say we put a piece of paper in with it, can it determine that it doesn't want this piece of paper versus an earthworm? I think that'd be pretty interesting to study, a further study and further investigation. And here's the reference. This is the article, so if anyone wants to read it, it's very, very interesting how the mole uses this star to touch, and then essentially it sees what it is touching in its brain. It's very, very interesting. And I hope you enjoyed my presentation.